Okay, yes, let's just start. And today, just before we start, just like to catch up on the homework and assignments. So we have homework 1, which is supposed to be due today at midnight. Okay, I think a lot of people have already submitted. Let me check. It should be. I should have there it is. Okay. Yeah, so people have submitted. All right. So if you haven't, then everyone has submitted. So then the next assignment is going to be homework 2, and that is due April 4th. Okay. And homework 2 will be about the perceptron. So homework 1, you know, is about the matrices. And homework 2 will be mainly kind of doing what we did last week. Yeah. Actually last week, the Jupyter notebook did more than the homework requirement. So if you went through the lecture last week, you should have no problem with homework 2. That being said, if people have questions or problems, do kind of email me or post on the discussion, on NTU Cool, and I will, welcome to discuss and address there. And actually, I think it'd be welcome because then other people might have the same questions or problems, and it'd be good for, sometimes you want to ask, you haven't asked yet, but other people have thought of it and asked, and then you're very grateful that they asked. So that you yourself also benefit from the, you're not alone first, other people also have the same questions, and also similarly, that they get the ball rolling, and then we can solve problems together. Okay, so today, we're not going to do any coding or, technically we don't need any computers even. We're just going to go through the theory about the Hopfield network, okay? And so, I don't know if we will take up all 3 hours. We'll finish whatever, and then we'll call it a day, and then we'll let our brains kind of digest things, and also use the time probably to, I don't know, just play more with the code or anything on your own time. Okay, so get this going. Yeah. So then today we're going to be talking about the Hopfield network. So just to give you some perspective, John Hopfield won the Nobel Prize, shared the Nobel Prize, okay, with Geoffrey Hinton for AI. They won Nobel Prize in physics, even though both are not physicists. So the physicists are a little bit weird about that, how come you're not physicists and you can win Nobel Prize in physics? But the fact is that what they do is on the level of computation that is, on information theory, on information science. And information science is kind of a gray area between, you want to say, mathematics or physics. I would say that it is really a fundamental for both. So technically, whatever you do in information science can be considered mathematics, computation, or physics. And in some cases now, you will even say relevance for psychology, actually. So even in things like, do they have a Nobel Prize for I don't know if there's no Nobel Prize for psychology, but a psychologist won a Nobel Prize for, was it chemistry or something? What? Economics? Yeah, I guess you could say that. That's kind of weird also, right? So you see, this Nobel Prize, a bit tricky. But the fact is that, yes, won the Nobel, they're computational neuroscientists, mathematicians, and they won the Nobel Prize for physics. But you see, today we're dealing with it from the perspective of neuroscience and moreover in cognition. So it's actually very fundamental, and it doesn't matter what field it's in. It deals with something that many fields are interested in. So, and specifically today, you will see that the Hopfield network, at least if you've read the paper, okay, you will see that actually the core problem that he's trying to address is one about memory, okay, and which actually is more of a psychological concept, right? So he's trying to see if a computer code or some sort of algorithm okay, can give rise to what we all take for granted every day, that we have memory, okay? And what is memory, and then like how does can it be computed? Can it be reduced to some sort of an algorithm, okay? If so, how, right, specifically? Okay, so let me start off by saying that today we are going to do a Hopfield network. We're going to work on the Hopfield network. So we are working on Nobel Prize winning work, okay? And at the same time, I will say that this is also known as a autoencoder. And you will see as we go along why it is autoencoding and what that means. And also it is an attractor. And you will again see why that is the case, why these terms are all talking about similar things, if not identical things, in principle, okay? In the way that the Hopfield network works, okay? All right, so the goal, or at least the goal that was set in the paper, and as we say in perceptron, in simulations or in neural network projects, we always start by identifying the problem, the issue, or the goal that we want, okay? And so for example, last week in the perceptron, the goal was like, well, we have these logic computations that we seem to experience. Like if we put this statement, and then we put this statement, and then we seem to be able to compute that if both are true, then this must be true, or if one is true, then it's not true, or in different scenarios, one is true is enough to make the whole thing true. So logic tables as a psychological computation, right? Last week, the perceptron was used to solve those problems. Here, and so that was a psychological phenomena, that we have some facts, and somehow we can put the facts together to give rise to some conclusions of further facts, right? But here is a different class of things, and the problem or the goal that was stated was, number one, there's two, okay? The first one is to solve the problem of memory, or to understand or evaluate the phenomena of memory that we have all experienced. I'm sure we all think we have memory, okay? And specifically, I will talk more about this in a bit. Content addressable memory versus indexed memory. And we will talk more about that in a bit, okay? The second goal is to address this phenomena of Hebbian learning. And we will talk more about that in a bit as well. We will unpack these two goals later on. Okay, so first of all, I always like to start this, and then we can get ourselves to challenge our own thinking. What is memory? What is considered memory? What would you consider to be a state where some system has memory or does not have memory? So for example, I don't know, it's a very Chinese philosophical saying, does water have memory? Was it some Kung Fu movie or whatever said that water has memory or something, and it's very ridiculous, like you unfreeze the ice and then the water can replay the whole movie or something. I haven't watched too many TV shows. Does water have memory? Can you say that a system like in a cup of water, does it have anything that you might call memory? No? Most people think no. Okay, let's put it this way. How about if I freeze the water, okay, and then I chip it, I hit it, okay, then it cracks. Is that memory? No? No. Okay. What is that? It's just water reacting to some physical forces. Is it? Okay. Well, think about it. Okay. So now I have a, inside there's a hard disk. I zap it with some electricity, I press some buttons. And so, and you know what hard disks are made of, okay? What are they made of nowadays? Used to be transistor tubes, vacuum, and you know, like flip-flop switches. I guess it's the same thing, just at a very, very small scale, right? But no doubt, still the same almost molecular or atomic level of those kinds of states. You perturb it, and the state is kind of captured. And we say this has memory, right? Because you turn it on, it's still the same state. It's the same thing as water, isn't it? Like you just zapped it or you hit it, and it maintained its state. Okay? So you would say this has memory, right? Okay, so go and challenge yourself. What really is memory, okay? Do you think that water, when you hit it with ice, when water is ice, let's say, and you hit it and it kind of changed its state, okay? And then you say it's not memory. But then when this one, you perturb it with electricity, you say it has memory. Okay, so what is the difference, really? Okay, go and think about it. Here's another one, okay? So water, which is fluid, okay? And you hit it, and then it just kind of just flip-flop back into, like, you can't retrieve anything. Okay, so no memory, or there's memory. Okay, so this is questionable, I would say, okay? I've talked about inanimate or things that are we categorically say are not alive first, and then we obviously go to more complicated things. But at least for things that are not alive, it seems like if things are at least solid or semi-solid, right, state-wise, you can do something to it. You can tear it, you can hit it, and it seems if it retains the result of the action, okay, at some level, right? If I apply some action to the memory state and it maintains that state, we seem to say, at least for certain things, we say it's memory, but it's not intuitive for us to say that, well, actually, if you say, I would argue that if you have the ice and it breaks, it's some sort of a memory, okay? But it's not the memory in the way that we would say psychologically, okay? So there's a distinction there. But we have to start there from the fundamental principle. At heart, it is about some physical thing changing its state and holding it over time, right? That's what the ice break is, and that's what the memory chip is. It's holding a state over some indefinite period of time. Okay, so if that is the understanding, at least for inanimate objects, they maintain a memory, okay, not a conscious one, let's say, okay, but at least they sort of maintain their state of recorded some event that happened to them, okay, then, and it's just a matter of time. So this one can hold it indefinitely for as long as the memory chip will function, you know. And if you break an ice, okay, it will hold that state, but until it melts, and then that state is lost, so to speak. Or if you tear a piece of paper, it will hold that state until it's burnt or, you know, diffuses over many, many millions of years. It breaks down into dust. Okay, so there's this notion of holding states, and then it deteriorates over time. Okay, and if you project that back to the water example, if we hit water, water flows back and all that, and then we say that there's no retention of state, so no memory. I challenge you to think that, well, there is, okay, maybe, but very briefly in time. It's just scale, okay? At least for some sub-millisecond when you hit it, the water is not yet completely lost the effect of you hitting it, right? At least the molecules of the water that were hit, at least for a very brief moment in time, hasn't yet diffused completely all over the place. It just takes, it just very quickly dissipated, that's all. So it's less stable, but it does have sort of like a memory, very, very instantaneous, brief one of things that have happened to it. So for things that are not alive, inanimate objects, when we talk about memory, we're talking about states of the physical item or the physical element over some moment of time, which can be very brief, which can, you know, be very long, all right? And then that's it. Okay? And moreover, how this memory is formed is simply by some physical action, some mechanical action that we acted on its constituents. All right? So that's that class of memory. Now, And if you appreciate that, okay, so go back and digest that, like challenge your notion of really what is memory, okay? We have a computer. The way that it is storing the states seems to have something to do with something more abstract. It's not just about the flip-flop gates, the transistors, on and off. Those on and off represent something about how we input that information in, right? So if I press a button, traditional calculator, I press 1, and then the logic gates inside, which are perceptron-like, okay? Logic gates inside, they turn on or turn off. That represents to us a kind of an insight or knowledge about the notion of oneness, being 1, or being 2, or being 3, okay? So, but does that hard disk or memory understand what its states mean? Does it, when it changes its state from, when we cause it to change its state from 1 to 2, from its perspective, is there any meaning to the different states? Yeah, it doesn't need to be aware. It doesn't cost it anything to be aware or not. But can we speak of any level of awareness or understanding? And that's where the distinction between inanimate and living things, for example. You would say it doesn't, right? It doesn't care, or it doesn't matter. It's just changing its states in reaction to your action on it. Okay? Same thing with the ice, right? It hits. You hit the ice, it breaks. Sort of the state of the ice molecules have memory of the action, but it's meaningless to it. There is nothing deeper than that, nothing more than that. So it's recording, sort of, its molecules have some recording of previous actions in time, but that's it, full stop, nothing more than that. Okay? Moreover, if you understand computer memory, how the binary code is encoded into this hardware, okay? If I have a string of bits, okay? So if I have a string of bits like 0, 1, 1, 1, 0, like that, okay? And I want to store it, I store it in the states of, I put it into this, this computer, okay? All right? And later on, I want to find it again, right? Let's say I encoded many things, 1, 1, 1, 0, 0, etc. Okay? I will put this in this position. Okay? And then I'll put this, I will put this in this position. And then I'll put this one maybe in this physical location. And then etc. So in other words, it's not like I just chip the ice. I chip the ice here, I chip the ice somewhere else, and I chip the ice somewhere else. All right? So similarly, I have a hard disk. I put that one flip-flop states in this position, and then I put another flip-flop state in another position of the physical hardware. Doesn't mean anything to the ice, doesn't mean anything to the hardware, okay? But later on, if I want to go back and kind of retrieve what happened, what do? I go back to that physical location, isn't it? I will say, wait, I wanted this. I remembered that I stored 01110 into this chip. So where was it? Well, it was in this position. So I'll go look for it, and then I can retrieve the whole 01110. Now I want to retrieve something else. Oh, I remember it was in this position. So I'll go there and retrieve everything. Okay? So that's how it works, because to the chip and to the ice, there's no meaning about the position or what was happening to it. It just happened to it, and it stayed there. That's it. Okay? This is what we call indexed. Okay? Indexed memory. Okay. Any question about this concept? So first, we're starting from very low-level physics, kind of, almost naive notions, and then we challenge ourselves. But then, at the heart of it, how all computers operate right now is like that. Can you think of whether something like ChatGPT or LLM, is it indexed like this?
It's more complicated.
You think?
Yeah.
How so?
I don't know, I just feel like this method is a bit too slow.
Slow in the sense of when you want to search and retrieve things, you think?
Oh yeah, ChatGPT uses slow.
I mean, you know, hash tables, we can talk more about that, but they can speed up search by very complicated algorithms, but, well, not so complicated algorithms, but they speed things up. But it solves like you don't have to search for index things serially. You can just directly go to it. It's very smart, but it's still indexed memory. It's still some sort of position with some label or key, okay? And it's a matter of finding the key to get at the content of that position, okay? ChatGPT, for all intents and purposes, as long as it operates on a chip, is like that. Maybe very complicated indexing, all right, but indexing nonetheless. For example, I train the weights of a neural network, right, which is what all these ChatGPT does. And then the weights are those flip-flop on-off states, right? How big, like, so for example, 1, 2, 3, on the calculator, the numbers are those binary codes. Those binary codes are put in a position. That position, the binary state, represents the weight of an LLM, right? When an LLM sees an input, so maybe I see cat, and when I say cat, it will, you know, I have an algorithm which will go to this. What does cat mean, or what does cat represent in the hardware system? Oh, it's this position, this whatever states that are in that position. Then the algorithm says, well, when you, after doing this, then go search for the next index. And then it will search this one, and then it will spit out meow, for example. Right? That's what LLM does, right? I give you a queue, a token. Just use this token, go search my space. Okay, this space and tells me, because it's all just numbers, and depending on what that number is, I go to another place, which is another number, which is another bit state, and I retrieve it, and then I just output something to you. Okay, so you can imagine, very, very complicated, obviously, but at heart, it can be done like that, in principle. Okay? So it's all memory, it's computer memory, it's index memory, because of the way it encodes things is I just change the state of a physical object, and just by doing that, I can do all these amazing things already. That's why computers are amazing, because actually, philosophically speaking, they're not really that complicated in the kind of what is going on sense. It's complicated in the algorithm and the implementation, but the heart or the core, the logic of it is actually okay. Okay, all right. So that's what we call index memory. All right. So what do you think? Any computer right now in existence that does not do index memory? I don't think so. Okay. Even quantum computers, that's debatable, but it still seems to be like it's about a physical thing having different states. That's all. Okay. So as long as it's a physical, inanimate object, it seems, okay, and then you perturb its states to encode something, to store something over an indefinite period of time, okay, before something wipes out the memory or whatever, that is index memory. And that's the distinction between your memory, okay? How are you different from this? Is your memory indexed? How do you remember things? If I give you cat, and then you retrieve meow, do you think your brain is like, cat, okay, go search for a state cat, then go find some meow thing? Is that how it works? By some position of where meow is, or where cat is, go find it, and then pull it back. Is that how you think your brain works? I think not, right? Yes? It's in doubt. Yeah.
I was thinking, I don't really know the exact
I don't know how is this code or whether it's the final index memory. If I split up two and do that, I understand already in the computer system now.
So you mean like if you teach it some or you show it something, it can do it again, like implicitly. It knows it has done this before. So in other words, the second time is easier or something like this phenomena. Okay, great insight. So there I ask you, if you have index memory, is there any reason why so-called the second time you get cat and then it gives you meow, that procedure will be faster using index memory? That's a great thing. Think about that logically.
I would say, as long as it's being reinforced, the indexing sort of like the weight thing will be, I think that's sort of like part mathematically. 2 times 2 equals 4.
Yeah.
And it's always like, at least in Chinese you always ruminate. And it gets 2 times 2 automatically becomes 4. It gets easier over time.
Right.
In that sense,
correct. So that's sort of what he's talking about. That yours is you are doing the 2 times 2 equals 4. First time, let's say you're 1 year old, 2 years old, right? Takes you 5 minutes, 10 minutes. Now it takes you less than 1 second, right? Does that happen in a calculator? 2 times 2 equals 4. Does it have this kind of, at first very hard and then it becomes very easy or faster? No, right? So index memory doesn't have that phenomena. It might be like a fake one, like in the operating system, if I set things up and then at first it was very difficult, but then now that I set it automated, I just click shortcut and then it's very fast. But that's strictly not what we are thinking about, right? It's not like I'm doing the same thing. It's more like I'm just creating another program to make my algorithm more efficient, that's all. But it's not the same as I do the same thing again and sort of automatically or implicitly we say it becomes more efficient somehow. We didn't implement any explicit code to give us shortcuts. It just became somehow faster, okay? And that's memory in the sense that when we did something, right, we remember we did it before. That's why the second time was easiest. That was easier. It's the only way to express that is that at least there is some memory happening of having done that before, right? Because other things that we didn't do before will take us longer, okay? Right, so, but that's not index memory, so that's not the way we function, apparently. It seems to have that difference. Okay, so very good insight, yeah.
Keyword memory in the sense is, yes, retrieval is, I would say, at least conceptually is indexing just association. But I think fundamentally the key difference is that there's an origin to that initiates the retrieval process, and that one it's at least distinguishes humans from what I would say like a computer system.
You mean there's an agent or something?
Yeah.
There's agency? Okay. You can put this concept up there. What is agency? So humans, we all agree we have agency. We might tend to think that a computer does not have agency. Okay, what does agency mean? It's hard. Okay? I don't know. I don't think people have a convincing, definitive definition of what agency right now is. We just know that we experience it, but it's very hard to define it. We can only define it more like what it does, but we do not know how or the mechanics of how it is done. Okay? So we can describe that we have agency because whatever, but the calculator does not have agency because whatever, right? But we do not know exactly when the thing has agency, so to speak, okay? So if you want to go the agency route to say like, well, we have agentic memory, whereas a computer or calculator does not. So do you think that ChatGPT has close to our level of so-called memory. So like now you can engage in a conversation with ChatGPT, and ChatGPT seems to sort of know what we are talking about for that moment, right? I start the session and I say, hey, I'm feeling kind of sad, you know, I want to cook something to get rid of my depression, you know, what do you suggest? And it can integrate all of that and then give me some sort of a reasonable answer, or at least I feel like it's a reasonable response. It's sort of close already, right? Arguably. I mean, if you don't demand too much, it's actually quite good, okay? Right? Okay. So, sort of a memory implementation there, okay? Almost agentic in a sense that it seems to have some, I receive something and I can control how I want to put some output, right? I'm not just reacting to things sort of passively. I am doing something at least deeper. Okay, so let me propose to you, one key phenomena is depth. Okay, and this actually goes back to last week's perceptron, that when you want to solve nonlinear problems, if you didn't know, you have to have what we call a hidden layer, a deeper layer, not just a single layer. Single layer perceptrons cannot solve nonlinear problems. Okay, you need multi-layer perceptrons, and we will come back to that when we do backpropagation. But the idea here is that you can sort of make your neural network exhibit sort of more almost non-index-like memory, okay? More like what we are trying to get at is agentic, that it seems to learn implicitly and all that, by adding depth to it, okay? And then it seems to be able to do something more like us, okay? But it is still indexed. It's still operating at some level. You can break it down. It's still operating on a hardware chip where it's indexing position and what's in the state of those physical constituents in that location, in that physical location. So as long as it's doing that, it is sort of indexing. Here is the key problem. The relationship, this is why it is indexed. The key definition is when a memory is indexed when the relationship between the state or the physical state, okay, and the content, which is sort of a psychological one, if you want to say, but whatever it is, let's not go there yet. The state itself and the content that it is encoded in it is arbitrary. Okay? This is the key sort of limitation or the key feature of index memory. In other words, it doesn't matter when I say cat, right? And I say I put it in this location, right? It doesn't matter if I put this 0110 on the first row or the second row or the third row or the last row. It doesn't matter. Because as long as I have the position, I can always retrieve 0110 and then use it to produce 01100. And it doesn't matter where 01100 is for that matter. It can be anywhere. It can even be broken up. Now there are more creative ways of storing. It doesn't all have to be in a sequence, right? It can be sort of distributed, but it's still the same thing, still the same concept, right? The fact it doesn't matter. That's why you can compress memory in a hard disk in very creative ways. It doesn't matter. You can still retrieve it. You cannot compress your brain memory, okay? Because your memory its content and the nodes, the neurons that were used to encode it, the position of it are not arbitrary. I cannot say I move this neuron and then I make it go to another neuron and the memory is exactly the same. Moving the neurons or changing the way the neurons work totally change the memory, even if it's just a little bit, okay? Whereas in a computer, it doesn't matter. I take this one, I put this one somewhere else. As long as I know it's there, I can still reinstate exactly the memory. So that's the difference. Index versus what we call non-index and what we call content addressable, okay, is because the position, the state rather, of the physical system, put it lower, the state of the physical system and the content itself, the relationship is arbitrary. Okay, so that's the key feature. So let's push this a little bit more. Yeah. So for example, if we understand that distinction, and then now we talk about the fact that we feel like we have what we call content addressable memory. What are the features of content addressable memory? Okay. So let me go next page. This is what we feel that we have. We feel like we have content addressable memory, okay? So a key feature is that if we change the neuron used or its state, okay? We change the content. Okay? It is by definition like that. So by that token, this is why kind of like offshoot, but clinical wise, okay? This is why when you get Alzheimer's disease, okay? And one of the things about Alzheimer's disease is the neurons die. They get lost. No more. Okay, the connections are gone. Even if the neuron doesn't die, the connections are kind of cut. And then you say that you give them a drug. All right, it's still not a cure because the memory is lost. Once it's lost, it's lost. Okay, it may not be lost completely, right? But technically speaking, it is never the same again, all right? In fact, if you want to expand it to all our experiences are never exactly repeated. We are constantly forming new memories and losing old ones all the time, okay? Because the fact is, okay, you can remember, oh, when I was a kid, I was on the beach, like, with the sun shining and all that. But it's not the same as when you were on the beach, on the sun shining, exactly, right? You only remember bits of it. And as time goes by, it degrades or it changes. And then you realize that, wait, I was never on the beach with the sun on it. It's a hallucination, right? I mean, that happens, right? So, no, it's my mom showing me a photo of me on the beach and all that. I don't actually remember it, right? So those kinds of things, okay? That's the weirdness of our content addressable memory, is that because our neurons are biological, they grow, they die, they change their state dynamically, constantly. We can't control that, okay? At least not just like by pushing some buttons so easily. I mean, you can change it, obviously you can shape it, but not in the same way as you would a computer. Our memories are therefore, the content follow. It's dynamic, it grows, it changes, it dies, and it cannot be reinstated. So even if you give clinical people, Alzheimer's disease, you give a drug, and you say that, oh, that's cured it. What it means is, or not say cure right now, but halt it or slow it down. What it means is that you prevent neurons from further death, or you prevent further cutting of the connections. But once what's lost, it is lost. The memory is lost. Which is why the best way to address Alzheimer's disease is when you are young and you have those memories that you stop the neurons from dying, then the memories can stay longer, right? But once the memory is lost, you have clinical and you give them a drug. I mean, it's better than not, but sadly, what's lost is lost, okay? However, there's hope. And this is exactly why, because of, you'll see in a minute, okay? Or maybe next week, we'll see. But the fact that it's content addressable and it's dynamic, although it's lost, it's never the same, but it has some robustness also, okay? Index memory. If the position is arbitrary, the physical state and the contents relationship is arbitrary. But if I just remove the information of where the location is, if I remove the index, no matter what the content is, I cannot access it anymore. It's gone. The whole chunk is gone. So that's why it's very dangerous, your hard disk. All you have to do is press one button and delete, right? Recycle bin, delete. That's it. It's gone forever. It's very hard to delete things in your brain also. So although things can be lost, but it's also very hard to lose them. So it's kind of the irony. Okay? This is the pro and con of the two kind of system. Index memory, arbitrary, fidelity is very high because you exactly retrieve the memory. Okay? And then there's ways to restore memory, but all that. But if you delete it, if you lose the index, then it's lost. This one is like the content matters and all that, and you can lose it, and it will change, but it also has its own robustness implicitly. Okay, so what are some features of content addressable memory? So, we already raised one thing just now. It has in this capacity to do implicit learning. Okay, that is, if it is first time you learn something, second time somehow you remember that because the state itself is the content. So the first time you change the state versus the second time you change the state implicitly is going to capture the fact that you learned the state before. Okay, so that's implicit learning there. Let's talk about our own memories. What do you think are some features that you find that in your own memory that the computer doesn't have? Or is it nowadays the computers are so smart it's almost human? False memory. We can have false memory. Okay, that's fine. We can do. But is it? Yeah, we call it hallucination. But is it hallucinating? Maybe. Well.
We can't know it's a false memory unless someone tells us.
I think, again, well, then it begs the question of what you mean by belief, and what technically do you consider a false memory, right? Okay, if we say that ChatGPT gives you hallucinations by saying things that are not true, okay, and reporting it to you, you are the one who believe it to be true. ChatGPT doesn't believe anything. It's just telling you what was a result of some statistical computation, okay? But in the sense, if your definition of false belief is that to report this as the answer, even if it was not an actual instance, it was just a composition of separate instances. You put it together into some new instance that did not exist, okay, and that's false belief. Yeah, then ChatGPT does do false belief, right? And because that's what we do too. We had some assumption, we had another assumption. Somehow our brains put it together, and our brains told us as an agent that we saw this when actually we never saw it, right? So in that sense, it's kind of equivalent, okay? But Does that any difference? I don't know. I'm not saying that we have answers, okay, but we can list some features we think are more salient than others.
There's one
Yeah.
that's like
Mhm.
more common in like image generation where fingers like humans will always have the framework of it say 5 or less. Whereas some engineers they do 6 fingers, 2
Oh.
fingers, there's one kind.
So what is that?
Like there's a framework that's like very constrained. Like
Yeah.
we cannot imagine what we can't imagine. Like it has to be reconstructed from something that we know of or something like that. Very hard to.
Or at least more constrained.
Something
Yeah.
is stopping us.
Maybe scale-wise, yeah. Like, well, we are constrained by our experiences. We are both constrained by our experiences, our brain and the ChatGPT. Whatever data you feed us, that is the constraint. But it seems that our constraint is more, whereas a machine's constraint is less. A big clear constraint that we have is we live in a physical world. We will fall down, we will die, we will bleed, we have pain. Computer does not have any of that. They only have ones and zeros as its constraints. Yeah. No one has tried to threaten ChatGPT if I turn off your power. You know, is that a bad thing? To it, it's like, oh, okay, turn it off, whatever, right? Yeah, interesting, right? But yes, levels of constraints is very different. That affects our memory. Our content addressable memory has that difference. Anything else? Nowadays, the lines are very blurred.
Also, at least to the typical computer, it's more malleable.
What do you mean?
Because, like, let's say, like in a computer, a file name, it always only has one name.
Yeah.
But sometimes we can call it the same thing has two different states, the same thing. But yeah, I think the LLMs then they already overcome this. But at least to a typical computer.
Let's just put a layman's term on it. We call this fuzzy categories. Or analog. Analogical. Yeah. Okay. Yes. Index memory is algorithmic. It's either right or wrong, technically speaking. It can express stochasticity, randomness, or some fuzziness, so to speak. But it is actually not randomness. It is still just specific different perturbations, but very well-defined perturbations, nonetheless. For our content addressable, because we, at least biologically, we experience more analogical states, right? We have much, in that sense, our what it means is we have higher resolution. Okay, at the current computation state, the resolution is at the level of bits. Okay, and as however small you want the bits to be, conceptually it's about bits, and the constraint of the resolution is how fine you can make your chip, how small you can make it. That is like the minimum unit, and so that's why quantum is interesting, because quantum will be more like us, because when you go there, you go below the 0-1 limit, and you go into probabilities, and that's where we sort of function, in a sense that when it's probabilities, although it is between 0 and 1, but it's the whole infinite kind of divisions between 0 and 1 that we are working with, so to speak, okay? And so when you work in that level, it is fuzzy, it is analogical, it is kind of very, very high resolution. Like changes in probability leads to big changes in the real instance, okay? So it's more quantum-like. If you don't really understand why this is quantum-like, you have to go and do quantum mechanics and quantum physics. Get some bits of understanding about what quantum mechanics or quantum physics is. A very simple placeholder I will put here for you is basically it's dealing with probabilities, okay? At let's say subatomic or sub. It's conceptual, okay? Whatever is between 0 and 1, okay? Whereas everything that is classical physics is up to the level of 1, the smallest unit. Quantum is about what happens if we go below that smallest unit. Does nothing exist there? The fact is there seems to be some phenomena. That's where the quantum level is, okay? So it seems we are functioning sort of at that kind of mode. It's not about size, it's about resolution, okay? Okay, so what you are saying, the implication there is that the fact is that for a hard computer like this, it is, even if you do random, the random is actually still very, very clear discrete state. Whereas what we operate seems to have much higher resolution and we can rescale, okay? Very, very flexible. So it seems more probabilistic actually, okay? So that's a very, very profound, deep insight, okay? And obviously this doesn't only apply to the fact of the phenomena of content addressable memory, but that it applies to pretty much every kind of computation that we do. Okay. All right, so I mean there are many features we can talk of, and I put forth to you that about 10, 15 years ago, right? we will have more features that are distinct from what a computer can do. But this list is getting smaller and smaller because of advances in AI. It's a fact. Okay? So in other words, and it is tied to this notion. It used to be that our computational power and the sizes of our chips are larger and the computational power is less. So the operations they do are like the bits are very coarse. So we were not satisfied. We can operate better than the computer on many problems. But now they compress things, so the scale is becoming smaller and smaller and smaller. So the resolution for raw hard drive computing is approaching quantum-like. In fact, they have quantum computers. So when that happens, suddenly all these things maybe start to drop off. You see the problem there? Well, not a problem, but the fact of what intelligence means, what cognition means, and the power of the neural network and these operations, how they come together. Okay? It's very intriguing to me. So I think we are only just now realizing this because of advances in technology, and then kind of giving us insight into, wait, what does it mean when we say that, oh, computers can do this, computers can't do this? You know, the lines are really graying, and what does that mean exactly and why? So this is one of those reasons, okay? All right, so when we say content addressable memory, what we mean is that instead of indexed memory, which is that the state the state is not equals to or is independent from the content, okay? Content addressable memory, okay? The state is a function of the content. And that's the key distinction here, okay? So for example, when I say cat, all right, and that leads to some neurons firing, okay, that neurons firing is exactly the content of cat insofar as my computation is concerned. Okay, so you have to kind of remove this notion that cat exists apart from your neurons firing. So if your neurons don't fire, then as far as your brain is concerned, cat does not exist. Okay, but if your brain fires in that way, that means that you are thinking about cat exactly. Okay, there's the equivalence there. All right, so that's the difference. Or at least that's the ideal of what we mean when we say content addressable memory. That the way that the neurons are firing itself is the address, is the so-called index of that memory. They are one and the same thing. They cannot be separated. Whereas an index memory, yes, you can. Okay? Any question about that? That's the key principle, the key distinction. And the challenge for Hopfield is, so this is ironic. We are saying that the brain does content, okay, and the machine does index. Hopfield is trying to say, can we make a machine mimic the brain to do content? And obviously the answer is yes, we can, but how? And what does that mean, right? Okay, we'll explore more of that later. Okay, but think about that. Okay, so content addressable, that's challenge number one, goal number one that Hopfield is trying to address. And so how does he address it, right? He uses the fact that he observed from Hebbian learning. So Hebbian learning, specifically Donald Hebb, very famously said, or very famously, who can recite what he said? Don't know? Oh guys, you guys need to read, okay? Then? No? No idea? Okay. From a neuroscience point of view, he observed that this Donald Hebb, not Hopfield, right? Hopfield was actually looking at Donald Hebb's work. And Donald Hebb, what he found was that, and this is in the NMDA receptors, okay? So it's like, for example, or synaptic dependent learning. Okay, the phenomena is that if you observe in vivo, if you can, or in vitro, you stimulate neurons and they fire together, they will start to form synapses, and so that the next time you stimulate this neuron, the other neuron will also get stimulated. Originally, they were not connected, but if you do that, they have this way of reinforcing each other to strengthen the connection, because if, oh, when I'm active, you're active too. Well, let's kind of like make connections. Yeah. Okay, so this is an observation, it's a fact. We do that, our biological systems do that. We know now that that's not the only thing that happens, right? But it's still very much established and accepted, okay? And so, does that make sense? Okay, and how does that work biologically? We can go into more detail, but you can go and read up Hebb. The idea is that when you get electrical impulses to that synapse, and they find that the other side also has some similar electrical impulses, you get some chemical signaling, okay? That weight, I think it's calcium or whatever, you get released into the intracellular, you get calcium signaling that happens because of the electrochemical potentials that are in sync, right? So the calcium signal goes and many mechanisms, but it causes the nucleus, the DNA, to express more proteins. These proteins are the receptors. Okay, then it goes back to the membrane, and then that becomes more synapse. So so there are more receptors now. So now I just need a little bit and then I will get the same more easily to fire. So you get phenomena like long-term potentiation, and also short-term. Okay, LTP, even LTD is sort of depression. Okay, it's a similar mechanism. It's basically the way your neurons adapt their synaptic connections over time based on the activity, either excitatory, common in frequency, or inhibitory, that conflicts, so that you reduce the receptor or you increase receptor depending on whether it's inhibitory or excitatory. Through these mechanisms, the brain, especially the hippocampus, okay, learns and remembers what has been happening in its immediate environment, in its other neighboring neurons. Okay, so Donald Hebb and other scientists did this biologically, and Hopfield is trying to model this, use this to see if we can, this phenomena that if you get two units firing together, or you got two states that are the same, okay, then reinforce it, okay? If they are not the same, then don't reinforce it, okay? And whether doing something like that can give you content addressable memory. All right? Okay, you got to remember when he published this, 1980 something. Yeah. At that time, having this jump from this to content addressable memory is like it's asking you to jump across the gorge. Like, how hard, there's no path, no way you can think of how to do it. It's this genius that he can do it. Now you ask us to do it like, oh, yeah, of course you can do it, right? Why was it that difficult? Yeah, right? So you really got to appreciate sometimes, okay? We take a lot of things for granted. But back then, to think about this and to make these connections, not so easy. Okay. All right. So this is, we spend a lot of time first to talk about this, and then later we'll go into more detail in a bit. But the fact is, the goal of Hopfield is to deal with this. You have this phenomena that our memory is different from a computer's. Specifically, ours is content addressable, and it seems like the way our neurons work is through Hebbian learning. How does Hebbian learning give rise to content addressable memory? This is the challenge of the simulation. Okay, so mapping that to the perceptron problem, we have the phenomena of we put two logical statements and then we give out some either true or false statements. All right, it seems that our neurons do this by having the notion of nodes and weights, connections to give rise, based on activation functions, to give rise to a subsequent neuron's activity. How does that setup kind of lead to the logic and AND gates that we do? Right? So that was the single layer perceptron thing. This one is now using the Hopfield network to do this memory thing based on these observations, these goals. Okay? So any questions about this? This is the very, this is kind of like summarizing the background or the motivation behind that paper. Okay, all right, so if not, we take a 5-minute break, okay? And then we'll come back and then we'll go more technical into exactly how he does it, okay? All right, so 5 minutes, we'll be back in, let's say 10, well, let's do 10:30, okay? So 10-minute break, okay? Okay, shall we start? Start up? Okay. So let's get into the meat of this. How does a Hopfield network use Hebbian learning to do content addressable memory? All right, having talked about the difference between content addressable memory and index memory, and going into what content addressable memory is. All right, so now let's, in order to do this, we will now go into specific computational examples, and this is where things get a bit more technical and into the meat of it. Okay, so content addressable. So we will turn this into a formal problem, just like in the perceptron. Okay, then from here, we will see how it is done. So we start, if we want to do content addressable memory using machine, using code, okay, well, let's run a simulation, okay, and see how that might be done in a simulation way. And if it is done in a simulation way, then we have some hope to do it, to see if that is indeed how it works in a biological real-life way, okay? But so let's do with simulation world in this course, all right? So let S be numbers of 1, 2, ... to n, okay? Let S be equals to 1 to n, and let them be sets of distinct states. All right? Or item features. That we wish to encode and retrieve based on item features. Okay. By that token, n is equals to length s number of states. Okay, so in expressing this formal statement already, I have kind of made something very clear. Okay, what is content addressable memory? It's memory in which if we encode its features, okay, that the memory has many states, okay, or many external information states to encode in its memory, okay? And content addressable memory is such that if we encode these features states, we can retrieve these feature states using these feature states, okay? And the key word here is themselves, or self, or auto, the notion of auto, myself, okay? That's why you will see this auto encoding coming out, all right? So in expressing this formal statement, this formal mission, that this is what we want to do, all right, or we have to do, we have invoked this concept that it has something to do with self. It has something to do with auto encoding, all right? Auto encode leading to auto-based retrieval. Okay? Essentially, that's what it is. All right? So then if this is the formal statement of the problem, we have S states from 1 to n. So, we have n sets of information that we want to write into this memory system so that if I give it now some parts of this state 1, it can retrieve the rest of state 1 because it is part of itself. State 1's set features are part of the set of state 1 itself. So to go further, let's make it specific. Specifically, we let s be equals to 1 to n, right? So specifically, let's say, or for example, I shouldn't say specifically. For example, we have a state called cat, okay? And that cat is made up of, it's defined by this vector that has these features: leaves, wood. Let's say we have these features: fur, tail, and meows. Okay? So if we want to say what defines a cat in this feature space, consists of these 5 dimensions, these 5 elements, okay? That it is, does it have leaves? Is it made of wood? Does it have fur? Does it have a tail? Does it meow? Then a cat in this feature space position, okay, is going to be, you can fill it up yourself, I hope. Yeah. Okay? Right. In fact, actually, it shouldn't be an arrow. Okay, we just let it be equals to that, okay? By the notion that the content is the state and the state is the content by equivalence. All right? We'll work through this example and you will see how the Hopfield network works. Is cotton a plant or a tree? Plant. I thought it's a tree. It might be a plant. I don't know. Anyway, let's assume it's not a tree. It's a plant. Okay. In this case, it doesn't matter anyway. So it has leaves. It has wood. It's furry. I would say. Does not have a tail. It doesn't meow. Okay. All right. So we have these states. 1, 2, 3, and 4, right? Okay, and that they are tree, dog, cat, dog, tree, cotton plant, and these states are embedded in the feature space of leaves, wood, fur, tail, meows. All right. So that is the information outside, but that we want to write. Into our system such that, okay, given leaves, okay, we can retrieve. Oops, spelling's really off these days. Retrieve Okay? So that's just saying just now in a sentence format. Now we are expressing it in a simulation, more formal coded mission here. I want to put this in a neural network so that when I then give this to the neural network, it will spit out this. Okay? So how do we do that, right? Okay? So it's kind of like the perceptron. I got 1, 1, and it gives me 1. 1, 0, give me 0, right? So I put it into a neural network. How does the neural network do that? So now I have my data table. This is my data table. Okay? So, this defines the data table like roughly. Okay? Okay. Now, just to have a point to note here is that if I do it this way, because I only stimulate, note, because I only stimulate like partial, like I have 1, 2, 3, 5 dimensions, right? But I only stimulate 1 dimension in the probe when I'm given probe. Okay, when I'm given the probe or the Q, okay, it's only partial, right? But even if it's partial, I somehow can retrieve the entire thing back. So there is this delocalization. Of representation. Probe, it's only this, but this gives me this. Okay? So from only one partial thing, I can regenerate the whole thing. Okay? That is a property of content addressable. Index memory cannot do that, strictly speaking. Right? I cannot say, if I index tree, I must have tree to find, I must have the position to find tree. I cannot give leaves and then sort of get tree. You can do that, but it's really more like an augmented use of the index, right? But at the fundamental level, if I want to find this string of bits, I cannot ask it to look for bit 1 and then it gives me the whole bit. It doesn't, right? There's no way to do it. I still have to retrieve the position. Okay? But content addressable memory can. It can do it. All right? So, how does it do that? So that's the data table informally, or at least semi-formally. Okay? That's the data table. So that was the next thing that we worry about, as with anything, because we want to do it with a neural network, then we define an activation function first. This is easy, okay? Because we are dealing with neural networks, as always, with a neural network, we need to have an activation function. And what's the activation function? It's the one that we had before, that AJ is equals to 1 if I'm going to use the arithmetic form, okay? But you can go ahead and think of it in vector form. A, I, K. Yeah, I'll write this out first, then I'll draw it out later. I, K, J, R. All right, is greater than theta is less than theta. You can do greater equals if you want. Okay, this is the threshold function or binary and it looks like this. Obviously, we've seen it before. This is and you implement it as okay. All right, any questions about this? This is the activation function that we will use. We can use any activation function. The one that Hopfield used is this one, because just need to make things binary, that's all, okay, for simplicity, all right? And this is what we dealt with this last week. What we didn't deal with last week was we didn't have an updating or a learning rule. And this is this distinction now for this week. So we have the activation function, but we must also have a learning rule, or some people say updating function or updating rule. Okay? It's a learning rule, it's an updating function, okay? Specifically, Hebbian. As we discussed just now, Hopfield used the Hebbian learning principle, or the Hebbian learning rule, which is that neurons who fire together in time wire together. They start to form connections. So what kind of function, so we will call this, the activation function we'll call equation 1, okay? What kind of function will make it such that the strength of the connections, okay, and by connections we mean this one, W, okay, what kind of functions will be such that if the activity of the units, the input and the output units are the same, then the W, the connection weights, will wire together, means it becomes stronger. Because if it's stronger, then it's more likely that this sum will become bigger. And if the sum value is increased, it will cross the threshold more easily, isn't it? And therefore lead to more activity. Okay? So whatever this equation is, whatever this function is, it has to achieve that. But as if the two are not the same, then there shouldn't be any change in the W. So what function does that? They have already a candidate, and that is that W, I, K, J, R is equals to, and we will unpack this later on, of some overall states. And we will see how that plays out later. But essentially, this is the key thing. My notation will be, I will put that, because S is summing over the 4 states that we have, cat, dog, tree, cotton plant, okay? So I'll put the index of S on top, all right? But this is going to be the input minus 1. Let me write that a bit more clearly. 2A input of the kth node for the S state minus 1. 2A output R, unit R, of the S state minus 1. Okay? And moreover, W, I, K, J, R is equals to 0 for K equals to R. And we will call this equation 2. Okay? Let me unpack it. This function looks very weird. It's like arbitrary. Why 2a minus 1, 2a minus 1, right? you'll see how it works out later on, okay? But the qualification is that the weights, okay, that connect I input to J output, okay, states, are the value that is of these weights, all right, will be equals to this 2a minus 1 function, except when that I and J are the same. Okay, if that's the case, then the weights is 0. There's no connection. 0 means no connection. Okay, so let's visualize this. Visualize. What does that mean? Okay, so note that my S is elements A I1. Oh, let me do it vertically. S is elements AI1, AI2, AI3, AI4, AI5. Okay? And this is state equals state 1. And then I have AI2, AI5, but for state 2, and then 3 and 4. Okay, what is this? This is cat, dog, tree, and cotton plant. Okay, I have 5 features that define these 4 states, right? These 4 pieces of information, and I code it such that these, for a given state, let's say cat, I have 5 input nodes, right? That will allow me to define cat. Okay, so then if I do it this way, yeah, so that n of S is equals to 4 states, which is the length of S. Okay, so some things to reiterate. K, which is the input number of nodes, is 4. 1, 2, 3, 4. Oh, sorry, and 5, right? And then R, which is the output nodes, is also 1, 2, 3, 4, 5. All right. And although we say output, what we mean is we have to qualify this. Input and output here refers to prior and posterior or subsequent states of node activity. Okay, it's not going to be like I have 2 nodes with a layer or whatever. It's more like I have a set of 5 nodes, and they are at first at some level of activity state, and then after some stimulation or change, they become another state. Okay, and that's why K is equals to R. It has to be. Okay, all right. To auto encode, so to visualize, we reiterate that what we have to do simply what that means is to make the output node state, okay, equals to the input node state, all right? And if I do not put the k or r, means I'm talking about the whole vector, okay, across k and across r. So this, right, this column is the vector ai, okay? Now, according to our equation, so I'll just drop the arrow. We understand that if I do not put the indices, then I'm talking about the whole vector, okay? We know that aj is equals to ai, yeah, multiplied by the weights, right, for any given one. But we want to make aj equals to ai, right? So, so that's the problem. What sort of w will allow us to make it so that after learning, aj becomes more like ai, okay? So then specifically, if I want to do the arithmetic form that the aj are, so if I put the indices, it's the arithmetic form over k, aik, w, I, k, j, r. Okay. Okay. And how do we visualize this? We have 5 states, right? So essentially, if you were to draw it out, bigger. 1, 2, 3, 4, 5. Okay, so this would be AI1, AI2. Okay, and this will be WI1, okay, but as far as this input node I1 is concerned, AI2 is AJ, the same state of the previous, is the input to it, okay? So actually it is the input, no, I shouldn't put it. It is J, it itself is J, okay? But it's receiving input from, okay, the second node to itself, okay? So let me rehash this with another one. This one will be AI3 to J1. Because if I'm AI1 right now, my later state will be AJ1, okay? And AJ1 is equals to the sum of the weighted inputs from AI2, AI3, AI4, AI5, correct? But not itself. So this right? Because when k is equals to r, there is no such connection. So I don't need to draw this, all right? I can just cancel this. This does not exist, okay? And then if I fill this all up, this is how I will visualize it. Okay, this is one instance. If I make AI the central node of focus right now. If I switch the basis, and I'll go to the next slide to do this, okay, and I'll do it in a larger picture. I'll do it in another instance. 1, 2, 3, 4, 5. And this is AI1, AI2, AI3, AI4, AI5. Okay, now I make this my focus, AJ2. AJ2 is going to be equals to WI2, WI1, J2, WI5, J2, WI4, J2, WI3, J2. Can you see it? All right. So if I cycle through all the nodes, basically, I'm talking about different reference weights. Okay. So this implies the full network looks like this. Am I missing something? Yeah, like this. Oh. Okay. This is what the full network is. In other words, you will have this case where the change in the weights, okay, is going to look like this. You have AI1, okay. When K, this is the I, and this is the J. Okay. When K is equals to R, then the weights is 0. So these are 0. Okay. When they are not, then exactly the change in weights is going to be 2AIK minus 1. Let me do it for, let's say, you can fill up this one, right? 2AI1 minus 1. Oh, sorry. And then this one will be 2AI2 minus 1, 2AJ5 minus 1, 2AI3 minus 1, 2AJ5 minus 1, etc., etc. You can fill up this whole thing, all right? Such that in basically the off diagonals are these 2AI minus 1, 2AJ minus 1 terms. Okay, so this is the array. This is the array W. Okay, relative to the vector J and the vector I, AI. You have these three variables that you have to work with, that Hopfield works with in his model. All right? And he gets this, to get to this kind of visualization and understanding of the arrays and the vectors that you have to work with, it's all there in his paper. If you read the paper, it's just a little bit hard to extract, okay? But this is essentially what's going on. All right, any questions about this so far? Yeah. All right, okay, so let's see how this plays out, this equation, okay? Here, where's my, okay, this one. Yeah, so great question. Y equation, what was equation? That was equation 2. So Y equation 2. Okay. Well, let's see how it plays out. We have a kind of a activation table, okay, based on the weights. Because it is going to be binary, it's either 1 or 0, this is going to be like our logic table again somewhat, such that there can only be 4 possible situations, all right? When AI is 1 and AJ is 1, work it out. What is Wij given the equation? 2 times 1 minus 1, so 2 minus 1, 1. 2 times 1 minus 1, 1. 1 times 1, 1. Okay? Okay? When it is like this, yeah? Okay. Interesting, right? Okay? So, in other words, yeah? When the two nodes states are the same, increase the weight. As long as one of them is different, decrease the weight. And when the two nodes state are the same, doesn't mean that it must be active. It could be both be inactive as well, but they are the same. They are equally inactive. So that will be considered the same state, and I want you to increase that information, that piece of information. But if they are different, then I want you to decrease that piece of information. Okay? So this equation, as it looks arbitrary, but it's not. It's a very, very simple binary instance of implementing this. All right? And in mathematics, I guess if you want to work this out, you will see that these derivatives and things and all that, we might be able to do a little bit of that, we'll see. But it gets a little bit complicated, and it's not really necessary, but we'll see. You will see that this equation is, if you go ahead and derive things, it does lead to what we call autoencoding, all right? And it does lead to that on average, no matter what states that you can say, because now we are talking about cat, dog, tree, cotton, plant, but technically the universe has infinite number of states, okay? But as long as we encode things in a binary way, this equation, when you work with its derivative, how it changes, how the weights change as a function of the different inputs change, on average, you will find that this equation will work out to be, if the states are the same, the expected weight change is going to be 0.5, positive. But if the states are different, it won't influence the weights. The weights will remain the same. And by implementing this, the systems representation becomes what we call the energy state goes lower and lower, which means that it tends to become attractor. It attracts different states such that it's easier to go to the prior learned states. Okay, we'll see how this plays out maybe in some of the mathematics later. But this is why he used this equation, so that this is the implementation of the Hopfield, the Hebbian learning. Fire together or don't fire together, wire together, right? Don't fire together, then don't wire together. That's what this equation does. Okay? Any other questions? No? Okay. All right. So let me ask you. So do you think just by looking at this setup, do you think it will work? Will this kind of setup achieve this? It's hard to see. Then that's why we have to run a simulation. We have to let it play out, because we will maybe go through some analytics later. We'll see. Even if I give you the analytics, it's hard to say whether it will work or not. Okay, and this is exactly the fun of it, the core of why we have to know these components and put it together, and then still have to run it, right? We make some good guesses, okay, but we still don't really know if it will work or not. It's hard to say, okay? So these are the steps. Okay, so are we on time? It should be good. Okay, so today's class, we won't really see it in action. So it's very hard to, like, what's going on, all right? But first, today we want to unpack the framework of the model. So the model components include those parts: the activation function, the learning rule, which is this one, 2a minus 1 thing, and then the architecture itself is, architecture graphically is like this, okay, visually is like this, but in vector matrix world, it's like this. You have a vector AI, you have a vector AJ, okay, and you have an array, a W array. This array is equivalent to this representation, such that these are connected. This is 0. This is all the weights, okay? And that is, if this is a J, then this is an I. Okay? This is the visualization that you should get. The Hopfield network is such that we have nodes, one node per feature that we want to encode. The nodes have a prior state, which is the input state, okay? And then it has a kind of subsequent state where the subsequent state is equal to the binary ReLU function based on the sum of the input states of the other nodes weighted by the connections, okay? And it doesn't connect to itself. So it doesn't have its prior state influencing its subsequent state. The only way that it can change its subsequent state comes from its neighbors, okay? So this is key. And the other thing is the W, okay, is a function of the input states a given node's input state with respect to the other node's output states, okay? 2AI is this current node's input state, okay? 2AJ is the other node's, 2AJ is this current node's output state, right? And no, I said it right, correct. 2AI is this current node's input state, and 2AJ is the other node's states, right? and then they will influence how much our weights will change. Okay? Right, so this is the setup. This is the architecture with the updating rule and the activation function. All right? So today, the key thing take home should be that. And why that learning rule is because if you work it out, you'll see this. Okay? Today, the key take home is this. All right, now I'm going quickly, or not so quickly, we'll see, into some proofs and derivations. There's going to be a lot of mathematics. Okay? None of this is essential. All right? It's just so that you can know how they think, how Hopfield think about why did I choose these equations in a bit more detail, okay? And what are some ideas that people should look out for when working with this model, all right? So here we talk about proofs. Architecture, the activation function, the learning function, proofs that the previous setup works. Okay? Proofs in a sense of how things will how things will evolve over time. Over time, or states of the input. Okay? And yeah, okay? So let's see. We began with this. So we go back to the notion that we want to auto-encode. Okay? We want AJ to be equals to AI. All right? We know that AJ is a function of this AI. And this Wij, Wij, is equals to Aik minus 1 and Wajr minus 1. Okay? So if we put this in, I had 1, 2, 3. So I'm going to say this is equation 4 and this is equation 5. Okay? We put and I'm going to say that, wait, let me introduce this as 5 first. I will develop equation 4 is also known as, specifically, not just proportionally, but exactly, it is the max of the sign of okay, that is the binary ReLU function. And then I introduce this, Wij is equals to 2Ik minus 1, 2Ajr minus 1. This one is equation 6. And so that if we put 6 into 5, we get Aj is equals to the max of the sign of AI 2aik minus 1, 2ajr minus 1, minus theta, 0. Right? And this one is equation 7. Okay? Simplify this is equals to, let's do the max sign function as basically that's equation 4, kind of like, but with more explicit. So we want to understand that Aj, simply put, is equals to the binary ReLU integration of the weights, specifically where the weights themselves are a function of the inputs themselves. Okay? So you can see how this thing is very dynamic. It's like the weights change because of the input, and the inputs change because of the weights. And so there is this dependency here. So that's why the mathematics is very tricky. Okay? So then if we go to the next one, note that for a given state, across all states, the activity, okay, of the output state of the neuron is going to be, if it's across all states, we sum across all possible states. So in our example here, we have 4 states: cat, dog, tree, cotton. All right. The activity of the node, right, is going to be, if you imagine that if you were to capture the total activity over, if I keep adding the information in, what is the net activity that this given unit is going to have? That's what this term means. Okay? So I sum across states, and I sum across the input k nodes coming in. All right? It's going to be a function of what I just had just now, where all states of the input k multiplied by all states of the weights, all right? For which it doesn't connect to itself. Okay? This is just re-expressing all of that, but just in more mathematical terms. Okay? And then if we simplify, you get ASJR is roughly proportionate to S. We take it from the, sorry, we don't simplify yet. Yeah, we don't simplify yet. We still keep it in its full form before we simplify. Otherwise, it's jumped too far. Okay, the function is, as we said, the function is basically the max sign. So we put that back. And we introduce the case of the states. Because previously we didn't talk about states. Okay, previously we didn't talk about states. Now we have this notion, because previously we are just talking about generically for a given node. But now we incorporate the notion that, well, note that actually it's also across states. All right, so we don't just sum across nodes, we sum across states. Okay, so this is kind of like moving forward from the just now that proof. Okay, so if that's the case, this is the expression. Okay, so this would be equation 7. This would be equation 8. Equation 8 is more general than equation 7. Okay, equation 7 is about a given node for a given input, but now for a given state. Equation 8 is like across all states, what is the expected or the total activity of this AJ rth node. Okay? Then if we expand it, because we expanded that, it looks very complicated and scary, we simplify it. Okay? Then yes, then now we can simplify that actually this is proportional to, the key thing is that is the sum over states still, but if you look at the function, all right, actually the only part that cares about the state, okay, is for the output, okay, it is because this is constant, right? This part is actually constant. The 2aj part is constant for a given aj. So you can take it out, okay, and then you put it there. And then the part, you can separate it, kind of reorganize things. The part that depends on the kth node is actually this part. Yeah? Okay? And in fact, you can view it as for a given state, we put an S prime here first. We can distinguish that there are cases when the state is the same, like when I have, like when I'm talking about cat to cat or cat to dog. So if my states, I have 4 pieces of information, 4 states of information, and I want to distinguish that, well, cat is not dog, cat is not tree, cat is not cotton, and dog is not cat, right? But dog is dog, okay? So I can make it such that the input states, I can distinguish 2 possible scenarios. One scenario is where the state is itself, so dog encoding dog or cat encoding cat. And another scenario is, well, now I have in my activation state, I want to actually distinguish what is cat versus what is not cat. Okay? So I can kind of jump out. This is a mathematical trick. Okay? I jump out first and I imagine that I have this equation, but I can imagine that there's 2 possible scenarios. So I put an S prime there first. Okay? So I have this now. This is equation 9. I set this up. And then I play it out, okay? Now, when S prime is not equals to S, so in other words, when I am encoding cat, but not dog, not tree, not cotton plant, okay? Current state, not with itself. So not self, okay, not self, not auto encoding, right? Then I have 4 states, right? Let's see how this is. Sorry. Okay. I have 3 columns because I'm talking about this one, this variable here. This one, and this one. Okay. So 3 things. When S prime is not equals to S, then if S prime, if AS prime I is 1, and if the input, so if AS prime activity is 1, okay, and the input activity is 1, then this term, because the two are not the same, is going to be 1. This is going to be 1 plus 1, I think. Did I get it right? Yes, right? 1. Okay? But when it's like this, it is going to be 0. When it's like this, it is going to be 0. This is different from the weights change. This is not talking about the weights change. This is talking about the total activity, the expected activity, given I have different input states to encode. Okay? All right? So don't be confused. It looks very similar, but you can see it's not. Oh, sorry, this is not 0. This is -1. And this is 0. Okay? Because the purpose here is different. It's not to show you that the weights are added or subtracted. This is to show you that when I have to encode things that are not myself, my average activation state, okay, is in this equation, I can expect that my average activation state is going to follow this pattern for the 4 states that I have, okay, and because my nodes can only take on 1s or 0s, there are only 4 possible situations, then I have this term here on the right will only possibly range from +1 to 0 to -1 to 0, such that expectation, okay, of S prime not equal when the expectation of the activity, output activity, when encoding dog versus cat tree cotton, the expected activity is 0. Okay, why? Because this plus this plus this plus this average is 0. Okay, right? The expected activity, mean of the AJ output is going to be 0. It cancels out, right? Okay. What this means is that this mathematics here, this complicated mathematics here, is telling us that when this network, because of the way the activation, because we set up this formula based on the learning rule and the activation function, right? Okay? And because of the way we set it up, and we implemented it such that the nodes are connected to every other node except itself, when we play this out, if we tell this network to distinguish cat from dog, tree, cotton, the output activity for this network, for the nodes, for any nodes, okay, with respect to if I am a cat node, right? Then if you show me dog, tree, cotton, my activity on average to dog, tree, cotton is going to be 0. My responsivity to not myself is 0. My expected responsivity. Sometimes I may fluctuate, but as long as I have many, many data points, on average, my responsivity to not cat will be 0. Okay? Got that? That's what this proof is about. All right? As I said, it's complicated. It's not really necessary, but I think it gives you some idea about how crazy these people work. But it kind of makes sense. Okay? Now, then consider the opposite case that when S is itself. So how do I respond when I'm a cat node, okay? And now you show me cat. On average, what my response will be. All right? So when current state is itself. Okay? So we take that form again. Yeah, when S prime is S, then you can do this. Yeah, you can combine them together. Correct? Only when S prime is equals to S, so that this term is 0 when the input state is 0, and 1 when input state is 1, yeah, obviously, okay? And which implies that the expected S prime equals S activity for the node is 0.5. 0 plus 1 divided by 2 is 0.5. Okay, because there's only these two possible states, all right, and their average, the expected value of these two average states is half. Okay? Moreover, question? Okay. Moreover, for the case where the states are the same, sum of k of that term above, okay, I'm going to drop the k here. I guess I have to put the k. This suggests this is a binary word of n bits. That's what this means. Okay, if you work it out, okay, you see that. Oh, sorry, I was wrong here. Not yet, not quite yet. This is not AI yet. This is just a. Yeah, I jumped too fast. The expected AI is 0.5, and that term 2AI squared minus AI. Okay, if you sum it over k, gives you n. All right, and the expected value of it is 0.5. So 0.5 times n. So this implies, I'm going to have to go to the next page. Sorry about that. I know the working memory is a problem. The expected value of Aj, okay, that's more correct, is equals to the expected, so when the states are the same, the expected value, because Aj is equals to the sum of j now. And this is going to be 2aj minus 1 nk 0.5. Okay, just a little qualification, just modifying the input. In other words, basically, when I am encoding myself, okay, the expected activity, right, it has to be a function of the number of nodes that I'm using to encode, right? I mean, I can't, because if I am just a 2-bit word, then my activity will be 0.5, okay? But if I'm a 10-bit word, then my average expectation, sum of all the activities, will be modulated by how many units I'm using to encode this state. So that's why the nk term has to be dealt with, all right? So it's not just simply, my input on average is going to be 0.5, okay? But because I have a few nodes, right? Then I have to first take into account, well, how many nodes are there first? So, well, it is basically that I have nk number of nodes to encode how many bits of the information that I have, and then I use that back into the expected Aj activity because I know that Aj is equals to WAI, right? And because AI is on average going to be 0.5, then I can use this equation to know just the average level of activity for when I am a cat node, right, and a cat state, and I am encoding cat states, then on average in my network, my activity level will be governed by this equation. depending on how many nodes I have, and my activation states, my activation output states, scaled by 0.5, half of that. Okay? Don't worry about so much about these proofs and mathematics. If you want to, you can go deep into them, but it is not necessary to implement the coding. All right? But if you do, I'm sure you will get more insights as you spend time to do it. Okay, now, there's the last few, one last thing. Any questions first about this? You don't worry about getting lost in the math. Okay, but I think the take home here is that we set up those equations and the architecture. And then because of that, if you're mathematically inclined, you can see that you can express these equations. You can use them. You can derive from them their derivatives. Okay, and or you can play some arithmetic about them, and you can see that because of the formula, because of the analytic solution, then you can predict that if I were to have different scenarios, right, what's going to happen to the network, okay? And these predictions tell us that, well, one thing, the network is going to have 0 level of activity when it is not encoding itself, and it's going to have whatever this result is level of activity when it is coding itself. So not non-zero, okay? And then it will also have the fact that the fact that you can see that especially from equation 7, okay? I think equation 7 is to note that essentially any given node's activity is a function of activities, because the learning rule for the weights is a function of activities. So any activity is a function of previous activities. So although we have this distinction between what's a node and what's a connection weight, a weight is really just some integral of activities. So then you can just basically express everything as activities. Okay? Right? So this, I think this is a key insight, like how to play with things, because you really understand where these numbers are coming from, okay, and what they mean. We will, when we come to backprop will also have some proofs. For the Hopfield, these proofs I think are trivial, are not so important. But the backprop proofs, that will be very insightful, because the backprop will, when you work out the proofs, it will lead you to the conclusion that backpropagation does gradient descent. Okay, and gradient descent is kind of like a minimization function that is universally applied, and and it magically pops out just because of the way we do backpropagation. All right, and there's a mathematical proof for that. But even though we do these mathematical proofs, as I said, there's still no way for you, even though we did this mathematical proof, for you to know whether the network really works or not, right? Right? Nothing in what we have done here tells you that, hey, wait. So does it really do the auto-encoding? Does it do the content addressable memory and all that? None of these proofs tell you exactly that whether they will do that. It just tells you that, well, on average, we can expect something like that. But really, does it really work? We're still not certain. So we still have to run the simulation. Okay? So if you read the Hopfield paper, you will see kind of these things coming out. Like there is mathematics and proofs and all that, but you still have to run the simulation in order to see if it works. Okay, so if we see if we run the model and we do the simulation and we want to know whether it works, then obviously the last part is we have to evaluate the model, and we won't, I'll talk about it today, but it won't be clear until we do it maybe next week. Okay? Evaluate the model. The last part. So having outlined the problem, proposing a solution, the architecture, the functions, going through how the model, the functions, and architecture works visually or graphically, and then maybe considering some mathematical proofs. We also want to preempt this idea that, well, when we get the model and we run the simulations, how will we know whether it's working or not, or how can we evaluate how it works, okay? We won't know how it's working. We will know how it's working, okay? We want this, okay. The first one is when we evaluate the model, we consider its energy, okay? Energy specifically, and I distinguish this from the expected value, okay? So to distinguish this, I'm going to say that this is, I'm just going to put a hat. So this is not energy, this is expected value, okay? But here we're talking about energy. Hopfield suggests that you can quantify the energy of the network, okay, at any time, all right? The energy that is inherent in the network. Okay. By this formula, minus half the sum of all the weights and the products with its activities. Why is this energy? And what is energy? Okay. Let's just say that equivalent statistical concept, okay, is variance. Okay, how variable the data are, right? Now, when something is very, very variable, okay, then the energy is very high. When something is not varying at all, it's constant, the energy is close to zero, correct? Okay, which one is a more stable case? High or low energy? Should be low energy, okay? Lower your energy, the more stable your situation is, okay? So this one, it proposes this formula because this minus half WAA, okay, is, you can liken it to the notion, I give you a form that you might be more familiar with. This is kinetic energy. Okay? The energy of anything that if I throw it moving, okay, is a function of how big it is, its mass, and how fast it's moving or accelerating in this case, by some constant, okay, half, okay, kinetic energy. Potential energy is mass, PE, this is KE. Right? How far away it is from a pulling source and its own mass. Added together, KE plus PE give you total energy, okay? But in a network, we care about is its activity. So it's kinetism, okay? How kinetic it is, okay? So if it is still very active, it's not good, okay? If it is like learn something, because if it is learn something, this will be minimized. All the weights are not all positive. The weights was actually kind of balanced out. So it actually approaches zero, right? No matter what the activity is. So in other words, if the network has learned something, this E value should go lower and lower. And because it's negative, it will be going lower than zero. Okay? That's the idea here. Because the proof is that if you do this, again, a little bit of math. Okay, if you work that out, it will be negative. you have the energy equation. If you differentiate it with respect to AJ, okay, then the result is negative. So like no matter what inputs I give you or what output states you are, your activity level will decrease. All right. I don't think that's important. Here, this is just to tell you that basically the energy is going to go negative. Okay. Another metric or evaluating component that we will consider is the Hamming distance. And the Hamming distance is defined as h is equals to the sum of k of aik minus ajk. Okay? And because the binary is binary, where ai is and aj are either 1 or 0, then these are just integers. Okay? And you can see the way the Hamming distance works. If my input state and my output state agree, then my Hamming, and they always agree across all nodes, then my Hamming distance is 0. But to the extent that one of them disagrees, right, then it's going to be more than 0. I suppose I should put a mod sign. Yeah, because it could be 1 is 0, 1 is 0, 1. The Hamming distance quantifies the binary extent to which two binary nodes, two binary vectors disagree. Okay? And so Hamming distance is another way to evaluate the model, right? Because if the model retrieves the memory I want, so if I give it leaves, I want it to retrieve tree, and it retrieves tree exactly, then the Hamming distance between the retrieved tree and what I want is 0. But let's say I give it leaves and it retrieves dog. But I want tree. So dog minus tree is going to have a bigger Hamming distance than tree minus tree. Okay? So that's this very simple way of evaluating the model. All right? So I introduced these concepts to you, and then next week we will be implementing some of the codes, okay, and then kind of playing with it, and then maybe the week after, over the 2 weeks, we'll see how this works out. And you guys will be having to create your own Hopfield network as well. And the assignment, which will be released at the end of this Hopfield section, will ask you to devise new problems. We'll give you some challenge problems to see how you solve it with the Hopfield network you will make. And then devise new problems or modify the Hopfield network you make. Just kind of like the perceptron that we did last week. Okay? But so we will work at this step by step. So for today, we cover these theoretical, conceptual backgrounds. Not everything is necessary, but it's just to give you a taste of, like, when you read these papers, this is what it's about. This is how they think. This is how we think. We should be thinking. Okay? All right. Any questions overall? Or many questions? It's okay. It's fine. You can see the assignment, okay? So build your own Hopfield network, okay? And this will be easier to digest when I can demo to you next week. But essentially, we are talking about, I will tell you that you have to build specifically a 16-unit autoencoder. What we have here in our board was a 5-unit autoencoder, right? 5 features, okay? And we will use, activation function, blah, blah, blah. And then there will be this notion of settling criterion on iteration. This has to do with the Hamming distance of a given state with respect to a prior state, that if the Hamming distance doesn't change anymore, then there's nothing else to learn. But as long as the Hamming distance is greater than 0, it means it hasn't learned cat yet, right? Because every time you learn cat, but some of the nodes haven't learned yet. Not all the nodes have learned. So some nodes need to be kind of like taught to like, wait, this is cat. Okay, you need to change it. I just told you it's supposed to be like this, but it still hasn't changed. Because there's some element of stochasticity in it, all right? Okay. And these are practical things we will talk about in the network. Then when you implement it, then you want to learn, have it to remember. These are the 4 states, okay? Can it retrieve state A if I give it partially something to do with state A? Okay? And not B, C, or D, because not state A. Then it should, on average, not respond to it. Okay? But if it is state A, then it should respond to it with a non-zero kind of response as a function of how many bits. All right? So there's also some level of sensitivity here. The more complicated my data is, the bigger my bits are, right? Then the harder my memory might have to work. But the fewer my bits are, then it's going to be easier to distinguish, right? Okay, so you have to think about that. There are these some sort of implications when you think about this. What is the psychological correspondence to what we are doing here in modeling world? Okay, yeah, so something like that. Then I'll ask you to create test patterns, train it, and then see, and then record like the Hamming distance and energy, and then from these simulations, describe what do you think this means, why is it doing that, and how does this relate to our psychological experience? Is this memory? Do we have such memory? Then you can also devise your own memory problem. Like, wait, I know that when we have memory, we have things like, for example, I think you sort of implement. You see these different patterns, okay? And I think I asked you to do some other patterns, okay? Across the patterns, we are actually trying out something like, what happens if, cat, dog, tree, and cotton plant, very easy to distinguish. What about Cheshire cat and like Siamese cat? Is it easier to distinguish than cat versus dog? We know that our memory has such distinction. How is that, similarly implemented? And you said, we raised the example just now. Our memory has this implicit way where we learn something by simply seeing it the second time, right? Then, or seeing it more times, then the memory trace becomes easier to access for us. What's the equivalent here? What is easy, okay, to the network, right? So things like that. When you have your model, you can sort of play with it, break it, and then see whether, to what extent it sort of mimics our psychological experience. Okay. Any other questions? Okay, so that's it for today, all right? It's very dense because it's conceptual, but when we do the actual coding and all that, the practical parts will become much more digestible, all right? So it's necessarily dense because it has to be. It's not easy, okay? No one said it's easy. The operation is easy, but the implication, the theory is not, okay? And we have to struggle with it, and we have to read the papers so that we understand where these scientists are coming from. Now, let's see. So next week, I will put up the collab of the autoencoder, and then we will go through it just like we did for the perceptron. And then next week, the homework 2 will be due, right? Yes. Homework 2 will be due next week, okay? Today, homework 1 is due, and then next week, I believe, homework 2 is due. Or is it the week after? Well, April 8th. 8th, yeah, after, yeah. So you have still some time. And then I would suggest that if you guys come, maybe you can hook up to the screens. Each of you take one screen, so that when you are trying things out, we can show everyone, or we can interact this way. All right. So since we have this future classroom, this is great because previously we had this where people are running code and then they have to look each other's small screens and check. Now that we have this, I think we can use it, right? And then let's try it out, okay? As we are running things, okay? So the next round, maybe when if you guys come early, you can feel free to go and set it up so that you can connect to the screens as well. So by that token, please, if you need HDMI, bring your HDMI adapters and things like that, okay? In case the Wi-Fi thing is very complicated, for sure, if you do HDMI, it should be the easiest way to connect to the screen. All right? Okay, so that would be it for today, and so no additional exercise or homework today. It's a lot to digest. All right, and just we'll see you next week. Okay.